Hey YouTube, this is my last video in my module on radicals and rational exponent notation, and I include this video because you can really see how using radicals can help you in situations where you're solving, say, polynomials of higher degree. So let's say I'm in a situation where we have a higher degree polynomial. So recall that the degree of a polynomial is the highest exponent on the main variable there, but we say we could solve this using rational exponents or with roots sometimes, and that is, in the particular case, you see the letter A here. We say solve this equation where we have 2x to the fourth power is equal to 162. We say solving this, we could just isolate the x to the power of 4 because there are no other x's to any other powers, and we could use a fourth root to undo that essentially. So I would say this, more generally speaking, the first thing we would try to do is set this equal to 0 and factor it. Okay, I'm just saying, and it does factor. But as a matter of fact, what I want to do is this, I want to solve it. So the idea here in this video is we're going to isolate the base of this exponent. So we're going to start by dividing by 2 here. And so if we were to divide by 2, we get x to the fourth power is equal to half of 162, which is 81. Okay, so we say 81. And then we say what we're going to do now, since we have this to the fourth power thing isolated, what we're going to do is we're going to take the fourth root of both sides. And recall that, if we said what's the fourth root of x to the fourth, it's really saying what could I take times itself 4 times to get x to the fourth? Well, it's got to be x. Okay, so basically this fourth root and fourth power, they undo each other. They're inverses. And we say, well, what's the fourth root of 81? I'm saying, really, what could I take to the fourth power to get 81? We say, was it 2? Not 2 to the fourth is 16, so 3. 3 times 3 times 3 times 3, that'd be 81. So we say, technically, it's plus or minus 3, but recall that because plus or minus 3 to the fourth power still gives you a positive 81. So we say the fourth root of 81, recognizing here that this was an even root, we'd say that we get plus or minus 4. Okay, and this would be easy to check by plugging back into the original equation. I do want to say that, at least, we say 162. If you were to put a plus or minus 4 back in here, we would get 2 to the, times positive 81 here, essentially. And by the way, why am I writing a 4 here? Sorry, this is a 3 the entire time. 3. I just got done saying 3. And I didn't write a 3. But yeah, so yeah, you could check this. We say 2 plus or minus 3 to the fourth power. This would be 162. And in this instance, you get 2 times 81, which is 162. And 162 equals 162, so this is a solution. Actually, we got 2 solutions. So now let's take a look at this other polynomial here. You notice that we have some base to the third power, and the base is some algebraic expression. But we could treat this just like we would treat something that says like x cubed, equals 10. In this case, though, we say that we would have to isolate the base, which we already have. We don't have like a 2 out front, or we're not like adding a 3 off on the side. So we are going to go ahead and we're going to solve this by undoing the power. We're going to do the inverse of a power. We're going to use the root. Okay, so we're going to use not just any root, but the cube root in this case of both sides. So we get the cube root of 10 on the right. And so we say, okay, so let's check this here. We get x minus 2 is the only thing that's left on the left, because the cube root of anything cubed is itself. We say this is equal to the cube root of 10. The only other thing we have to do is add 2 to both sides. Now I do want to comment on this. We'd say that we got the cube root of 10, which I haven't evaluated yet. We say plus 2. We're going to put a big fat box around this. We're going to call this an exact value. Okay, so an exact value as opposed to an approximation. Let's comment on this. An exact value is some simplified expression that represents that if you were to put this into a calculator, you get this exactly for the answer. As a matter of fact, if we plug this back in to the original, oh man, I'm going to do this here. We say x minus 2 to the third power equals 10. If we were to take this expression and put it back in here, that is the cube root of 10 plus 2. I want you to see that, first of all, these 2's cancel out, and we would just get left with the cube root of 10 on the inside of this, and we're cubing that. And we'd say, well, the cube root of 10 cubed. This cube root and the cubed cancel out, and we say we get 10 equals 10. So exact value means literally that. You get the exact value. Now, what we also want to get is an approximation, or at least a decimal approximation. So the way we're going to do this is we're going to get our calculators out. We're going to say 10. Now, the interesting thing here is we could write this as 10 to the 1/3 power plus 2, or sometimes your calculator gives you a cube root button. So we say the cube root of 10 plus 2. We get 4.154. So x now is approximately 4.154. And this right here, and I'm going to say ish, is an approximation. Okay, because it's not exactly what you started with. Now, I want to check this one as well, And in the original equation, we said it was x minus 2 cubed equals 10. We're putting this in for x. If now I were to put this in 4.154, let's talk about the validity of a decimal approximation here. Essentially, we would get 4.154. I'm even going to kick out all those decimal place values there. We say 154 only. And we say subtract 2 from this, and I want to cube this. So we say to the third power. So I get 9.9939, so on and so forth. And why didn't I get exactly 10? And the reason why is because I only used, 3 decimal places on this. So if you want to be more accurate, use the exact value. If you need to be precise, use the exact values. If you need to be somewhat precise because maybe you're finding a distance or something like that, then just use an approximation. Cheers.